Why do we learn graphical vector addition in high school when adding vectors together through components can be both faster and more accurate? Today we're going to solve the same problem with both methods and then cap it off by using unit vector notation. Welcome back to D215. In today's video, I'm going to be adding the same two vectors with all three methods. That way you can see it doesn't really matter what method I pick, they're going to give me the same result. I do need to answer the question though, why we care about vector addition in the first place. If you're ever dealing with an object that may have multiple forces acting on it at the same time, or you want to know what the net displacement of a person after they've changed directions repeatedly, or perhaps you might care about how a swimmer attempts to cross a river when there is a current. In each of these situations, we want to be able to boil down all the vectors acting on that object down to a singular vector we call the resultant. That's where vector addition comes in, us finding the net result of multiple vectors. In high school, we began with graphical vector addition because it was an effective way to teach students what vector addition should look like without actually requiring them to use a calculator. Here we can add vectors together using a protractor, ruler, I'll use a square, and doing some drawing. Now, to add vectors together correctly, we need to do a couple things. First, begin with a Cartesian coordinate system and establish a scale. I didn't want to include units like newtons or meters or anything really, because I wanted to show you that this was true regardless of the type of vectors you were adding together. Now, to put vector 1, or A, down, I first have to determine the direction. I know it should be at 53.13 degrees in the first quadrant, so I'm going to take my protractor, line it up with the y-axis here, and put 53.13, which is right here, indicate it with a little dot. Now, you probably noticed on my protractor that it's a teaching protractor and there isn't a lot of precision. That means there's going to be error in my answer. I'll do my best, but I know I'm not going to get the perfect answer. Next, take your ruler, or in my case, a meter stick, and I'm going to connect the origin with this dot, but make sure it's only 20 centimeters long, because the vector is 10 and my scale is 10 would turn into 20 centimeters. So let's go ahead and do that. So 0 gets the origin, I go up to the blue dot, it should be 20 centimeters, or right there, and I am going to put an arrow on the end because it is a vector, and I do want to represent that, but make sure you don't add any distance with that vector. And what we've just done is represented vector A. Now, to add vector B, we don't go back to the origin, but we add it to the end of vector A. And given that we don't have a Cartesian coordinate system there, we can get some more error. Most students just estimate where to put the protractor at this point, and you'd probably be close enough. But I want to be a little bit more precise, so I'm going to take my square, and I'm going to make sure I can get a horizontal line at the end of vector A. That way I have something to line my protractor up with. Then, taking my protractor, putting it at the end of vector 1, and using that new horizontal line I've just formed, I can put another dot, this time at 143.13 degrees. 143.13, right about there. And repeat the process of taking my meter stick, connecting those two dots, but this time only needing to go 10 centimeters. Now I have vector A and B. To add them together, graphically, all you need to do is connect the origin with the end of the final vector. So let's go ahead and do that. I'm not concerned with the protractor just yet because I'm not getting the answer, I'm just representing it. So, right about here, you can see I've actually added a little bit of error by not going right on the origin. But there we go. We've got our resultant vector. Now to get the actual answer, I'm going to measure it out. I see that I get about 22 centimeters. With my scale, 22 centimeters turns into 11. And to get the direction, I take up my protractor, put it on the origin, see where it lines up with the final vector. That's at about 80 degrees. And I can say my resultant vector is at 80 degrees, which means vector A plus vector B would equal 11 at 80 degrees. That was our first method of adding vectors together. The second method we'll be using today is adding vectors together using their rectangular components. It has the advantage of being more accurate, it'll be faster once you get the habits down, and we don't need to use a protractor or ruler. It does require some math though. Now I do have a Cartesian coordinate system up here so that I can establish the angles and directions more easily, but we're not drawing it to scale. I'm not going to use a ruler. There's vector A, and vector B should be going to the left, right about there. Again, that's just to help me with directions and angles. Now, to find the components of vector A, I need to figure out what its x, or its horizontal, and its y, or vertical components are. And we happen to know the angle right there is 53.13 degrees. At this point, the math isn't too hard. I can say that the x component of vector A is the magnitude of A multiplied by cosine theta, because the x component right here is adjacent to that angle. When we do this out, 10 times cosine 53.13, we get 6. Now the y component is opposite this angle, so it's not going to use cosine. Its y component would be magnitude of A multiplied by sine theta. And when we do that, we get out 8. Now vector B is a little bit more interesting because it's not in the first quadrant, which means it could use a reference angle or a standard angle. The standard angle would be the 143.13 degrees because it builds off of 0 at the positive x. That's 143.13. And you can use this along with some cosine and sine functions to figure out the components here, and it will tell you the direction at the same time. It will tell you if it's positive or negative. Most people don't learn it this way. Most people find it using what's called a reference angle, an angle right there. And that's fine. It'll still give you the right answer, but it'll always be positive, so you need to manually go in and add the positive or negative if the vector needs it. And in this case, the x component of B should be negative, so I'm going to have to manually put in that negative if I use the reference angle, and I will. The reference angle here, reference, would be 36.87 degrees. So I won't be using the 143.13, I'll be using this reference angle. All right, same step. Here's my x, here's my y. Let's figure out the x and y components. Bx, magnitude of B, cosine of my reference angle, to equal -4. Now, the function didn't tell me -4. It only told me 4. I had to manually go in and put the negative. By would be magnitude of B times sine theta, and this will be 3. And what I have now are the components of both vectors. Now this can be a lot of information to look at, more so if I had a third, fourth, or fifth vector. So I want to create a table to organize my information quickly. We can say vector A, vector B, and its x and y component. I can just put the values in. The x component of A is 6, the y is 8, the x component of B was -4, and the y component of B was 3. Now, this is starting to get like a lot of information up on the board at the same time, so I do want to erase a few things. Here's what was important anyways. Now it's called vector addition for a reason. I'm going to add the components together. Those new values are the components of my answer or resultant vector. We often don't want to just leave it here. Teachers often want to see a final answer, so I am going to have to figure out what the resultant vector is, not just its components. To do so, I am going to draw a small, little, new Cartesian coordinate system out so that I can establish a direction system for that resultant. We know we're going to the right 2 units because it's positive, 2. And we know we're going up 11 units because the y was also positive. So we know the answer has got to be in the first quadrant. Connect those, we've got our resultant vector, and some angle we need to figure out. Now that forms a right angle triangle, so we can figure out the magnitude of the answer, by using Pythagorean theorem. Rx squared plus ry squared, take the square root. When you put in 2 squared and 11 squared and square root them together, you get 11.18. Now, that's only the length or magnitude of that vector. We also need the direction. That's what the angle is going to help me with. I can find the angle easy enough with inverse tan, arctan, y over x, because I have y over x. I put the angle so that the x component was adjacent to it. And when we put 11 over 2 and use that trig function, we will get 79.7 degrees, which means we have all the pieces to our answer. We just need to put them together. We know that vector r equals 11.18 at 79.7 degrees. What I hope you're noticing is that this was very close to the answer I got with method 1, graphical vector addition, but it's just a bit more accurate and precise. The final method we're going to discuss today is adding vectors together using unit vector notation. Now, because we're using the same vectors for every example, I already know what the components are. I didn't want to have to redo that math. But I do need to turn these vectors into their unit vector notation. Now, it's simple enough if you already know its components. Vector A must be 6i hat plus 8j hat. It's x and y components. And vector B must be negative 4i hat plus 3j hat. Now, because this is vector addition, what I actually want to show is that my resultant vector must be vector A plus vector B. So A plus B, right? Now, if we were to break these out, it should be 6i hat plus 8j hat add negative 4i hat plus 3j hat. It doesn't look particularly simple, but note, I could just factor out the i's and j's and combine my terms, right? This would turn into 6 minus 4 I hat plus 8 add 3 j hat. Well, now it's a pretty simple set of operations. We know that this must be 2i hat add 11 j hat. That is vector A plus vector B using unit vector notation. Today's video focused on adding vectors together using 3 methods. Graphically, so you could visualize how vector addition looks, rectangular component addition, so you could compute them, and then unit vector notation, so you could extend them into 3 dimensions if you needed to. Now, our next few lessons will focus on the dot and cross product, and as always, I hope you have a wonderful day.